We've been using rate laws, like this generalized example here, for quite some time as a way to represent what we know about a reaction pathway. In particular, we looked at the mechanistic knowledge that can come from knowing which compounds appear in the rate law and the orders of those compounds. Now, we used that information about those particular terms in a way that let us determine what the potential energy surface, that is the reaction coordinate, might be. And along that reaction coordinate, part of what we found was that there was often some activation energy that maybe told us about the rate determining step. But here's a question that you might have asked yourself. If that activation energy is so important and it tells us so much about the rate, where is it in the rate law? We're now going to talk a little bit about how that activation energy appears in the rate law, and we're also going to start to explain the role that temperature plays in reaction rate. If you think back to the example of phenolphthalein and sodium hydroxide reacting near the start of this chapter, we saw that two features could be used to control reaction rate. One was concentration and the other was temperature. Now, with rate laws that we've seen so far, we have a pretty good idea of where concentration is showing up, but we haven't seen anything that yet accounts for temperature. So what we're looking for is some aspect of this rate law that's going to bring together what we know about activation energy and about temperature in a mathematical way. That's going to turn out to be the Arrhenius equation. The Arrhenius equation is going to be telling us about the rate law constant. Now, that rate law constant is a little bit misnamed in the sense that, as we're going to see, it's not really much of a constant. I mean, among other things, I'm already writing it as temperature dependent. But let's take a look at the Arrhenius equation and what it tells us about this reaction. The Arrhenius equation is as follows. Our reaction rate constant is equal to A times E to the minus EA over RT. Now, looking at this particular equation, there are a lot of unknowns in here. So, or I should say a lot of symbols anyway. Let's break down what each of those means. Well, E, that's something we've seen already, right? That's our exponential. Not too bad there. And this E to something, in this case, our activation energy, over RT, that actually looks a little bit like the equation that we were previously using to bring together equilibrium and thermodynamics. This Arrhenius equation, because of this RT component, is one that is fundamentally related to the ideal gas law. That's weird, right? Well, let's think about what this equation is really telling us. It's saying that our rate is equal to some constant that we'll talk about in a minute times the exponential of the opposite of the activation energy over RT. So if we're thinking about some molecule moving around in the reactants well over here, and the chance that it's going to make it up to this highest energy point, well, that's going to depend on the temperature. This whole exponent is negative. So if the temperature gets bigger, that exponent gets less negative. That means the exponential function gets bigger and our reaction goes faster. What that's really telling us is that at higher temperatures, our molecules are bouncing around more. Think back to PV equals nRT, for instance. In that equation, if we raised the temperature and didn't change our number of molecules, then either the pressure or the volume would have to go up. The molecules were bouncing around more. They were bouncing off the sides of the container and either exerting pressure or expanding it. It's not exactly the same thing, but you can kind of conceptually think about those reactant molecules bouncing around in there more and more, and so as they get to higher temperature, they have greater chances of popping out of that well and going over to become products. The activation energy is in the numerator of this fraction. That means that when the activation energy is bigger, this is more negative, and this exponential gets smaller. So the bigger the barrier height that has to be cleared here, the slower the reaction is going to go. Last but not least, we have this A value out front. That A value is called the frequency factor. And that frequency factor is basically answering the question, how frequently does a productive collision between reactants occur? If you think about two reactants reacting together, they might need to approach each other at some particular geometry. When we were looking at the case of some of the nucleophile-electrophile reactions, for instance, we saw that the nucleophile needed its lone pair to overlap with to donate into the empty orbital of the electrophile. That means that if the two reactants bumped into each other, but at the wrong angle or the wrong geometry, a reaction won't necessarily occur. So information about shape is partially encoded or partially included in that frequency factor. But this means something that's really, really important. It means that as complicated as this pathway may be, because that activation energy is representing the barrier that has to be crossed, we really only have to understand the geometry, both in terms of shape for frequency factor and in terms of the energy associated with that shape for the EA, in order to understand the rate of the reaction. We'll often refer to that highest energy point, that is the point that has that EA, as either the activated complex or my preferred concept or preferred way to describe it, the transition state. And we've actually already seen an example of a transition state. That structure that we looked at in the case of the SN2 reaction where chlorine was having its bond broken while the hydroxide attacked at the same time, that structure for SN2 was what we would call a transition state. And we often symbolize it with this double dagger formalism. Understanding the nature of that transition state can tell us why particular reactants are reactive with one another, and can also help to explain why a reaction has the rate that it does. The last thing I'd like to note, while we're on the topic of rate, is that if we look at the relationship between our rate constant and temperature, we observe that in general, our rates are going to go up exponentially with temperature. So at 0 Kelvin, this tells us that no reaction should be occurring. In essence, if the T here goes to 0, this whole fraction goes to infinity, and e to the negative infinity is going to be effectively 0. The result will be that our rate constant will go to 0. It should make sense that at 0 Kelvin, where no atoms can be moving, that our rate should be basically 0. If atoms can't move, they can't react. That also means that as the temperature goes up, our reaction speeds up. A general rule of thumb that many organic chemists use is that for a lot of common reactions, going up by 10 degrees Celsius, the same as 10 Kelvin, will typically result in doubling the reaction rate. The Arrhenius equation is a really valuable tool for understanding why reactions behave as they do. It also means that if we can measure the rate constant at a few different temperatures, we can actually determine the activation energy.